Let's jump right into this. Today we're taking a look at the physical reality of data centers, specifically unpacking the new Xinma 2026 data center cable tray guidelines. Now I know, cable tray guidelines, it sounds incredibly technical, but think about it for a second. Literally every video we stream, every transaction we make, all of our cloud backups, they all depend entirely on the physical cables strung up above those servers. Getting that layout right isn't just some minor background detail, it's the absolute foundation of keeping the digital world running smoothly. And while engineering guidelines might seem dense on the surface, if you look closely, they offer some incredibly practical, common-sense advice. So whether you're an installer with boots on the ground or a facility manager overseeing the whole operation, we're going to skip the heavy jargon today. Instead, we're turning these engineering principles into simple analogies and actionable insights. I promise, by the end of this explainer, you'll never look at a server room ceiling exactly the same way again. Okay, let's start with a really common scenario. Imagine walking into a modern data center. You check the thermostat, or maybe you just feel that conditioned air blowing up from the floor tiles, and it's a perfectly crisp, cool 24 degrees Celsius. Feels great, right? Naturally, you'd assume that because it feels perfectly cool to you standing down there on the floor, everything in that room is happily chilling at that exact same temperature. But is it really? Is your data center a perfectly cool 24 degrees everywhere? I want you to mentally look up. Look past the server racks, right up above the hot aisle where all those critical cable trays are suspended. The physical reality up there is a completely different story. What's actually happening up in the rafters is kind of wild. Right above that hot aisle, the air is absolutely not 24 degrees. Those cables are sitting in what engineers call a thermal plume. You know how heat naturally rises, right? Well, as high-powered servers continuously blast out hot air, it funnels directly upward. And because of this chimney effect, the temperature right where your delicate cables live is actually 5 to 12 degrees hotter than the room's set point. Just think about that. You might think your expensive infrastructure is resting in this climate-controlled haven, but up there, it's actively sweating. And it turns out, ignoring this thermal plume leads to some major downstream problems, because trapped heat is basically the enemy of infrastructure. We can really just think of this thermal plume as an invisible oven. And when cables sit continuously inside this oven, it fundamentally changes their ampacity. Now, let's just strip away the engineering jargon for a second. What is ampacity? Very simply, it's just the maximum amount of power a cable can safely carry before it starts to overheat, degrade, or worst-case scenario, become a fire hazard. When you stick a cable in a hotter environment, it simply cannot shed its own heat. It's exactly like trying to cool off after a grueling run while you're sitting inside a sauna. Because the cable can't naturally cool down, its safe carrying capacity, its ampacity, drops dramatically. Okay, let's dive into this and see how our practical, boots-on-the-ground hardware choices impact this invisible oven. You basically have two main options for cable trays. On one hand, you have a solid bottom tray. Putting a completely solid tray over a hot aisle is exactly like slamming a heavy, tight lid onto a hot oven. It completely traps that rising thermal plume, suffocating the cables and causing massive power capacity drops. On the other hand, you have a ventilated tray. Choosing this is like finally opening a window in a stuffy, overheated room. It lets that thermal plume flow freely right through and away from the cables. So the practical takeaway here is incredibly simple. If you want to solve heat flow, you absolutely have to let the system breathe. So heat dissipation is crucial, but so is order. Let's look at how this builds into the physical layout. In high-end Tier 3 and Tier 4 data centers, you can't just toss all your copper and fiber into one giant messy pile. The Xinma guidelines mandate strict segregation. Just picture your tray system as a highly organized 3-lane highway. Over in the first lane, you have the power lane. These are your high-voltage cables. Think of them as the heavy trucks of the highway. Next is the network lane. These are your delicate, high-speed fiber optics, the fast sports cars. And finally, the life safety lane for critical fire alarms and security. Those are your emergency vehicles. You have to keep them rigorously separated so they don't physically interfere with each other or cause a massive headache during maintenance. Now, to keep these highway lanes separated, installers will often drop metallic barriers right inside the trays. But this is where you have to make a very deliberate, practical trade-off. The big benefit of a metallic barrier is that it drastically improves EMC, or electromagnetic compatibility. In plain English, that metal wall stops the heavy trucks in the power lane from creating electrical noise that scrambles the delicate signals of the fast cars in the network lane. It gives you clean, reliable signals. But there's a cost. Every time you insert one of those metal walls, you lose usable physical width inside the tray. You literally have less room for cables. So if you're the one installing this, you have to weigh it out. Do I need maximum signal shielding right here, or do I need maximum physical space to run more lines? All right, we've organized our cables, we've managed the heat. Now we have to talk about weight. Modern data centers use massive trays, sometimes spanning 300 to 900 millimeters wide, packed with hundreds of pounds of copper and fiber. I want you to picture a heavy, completely soaked clothesline. If you string that wet clothesline between two poles that are just a little too far apart, what happens? Physics takes over, right? It naturally bows and sags deeply in the middle. The exact same thing happens to a fully loaded cable tray if your support brackets are spaced too widely. These structural load rules exist to prevent that dangerous sagging. Because a sagging tray doesn't just look unprofessional, it can literally warp the metal and stretch those super delicate fiber optic cables inside. So, what's the practical fix for this heavy clothesline problem? The guidelines actually give us a remarkably straightforward installation tip. Step 1, do not just blindly accept the default support spans listed on some generic blueprint. Actually look at the real, tangible weight of the cables you're about to load in. And step 2, simply move the support brackets 0.5 meters closer together. Just half a meter. It seems like such a tiny, almost insignificant tweak to make while you're bolting things to the ceiling, but the mechanical impact of tightening that span is absolutely massive. And this brilliantly illustrates just how impactful a tiny change can be. By bringing your supports just half a meter closer together, you effectively cut the structural sag of that cable tray by an astonishing 30 to 40%. I mean, that's like magic. You go from a stressed out, drooping setup that threatens to snap your cables to a tight, rigid, incredibly professional installation that will hold up for the entire lifespan of the facility. This is the perfect example of working smarter, not harder. You weren't buying radically different materials, you're just adjusting the math by half a meter. And it's really worth pointing out where these practical guidelines actually come from. They originate from Xinma, which is a leading global manufacturer of intelligent cable management systems and seismic bracing for massive infrastructure projects, everything from sprawling data centers to complex rail networks. These aren't just arbitrary tips thrown out there. Their products and the guidelines we're talking about today strictly adhere to top-tier global standards. We're talking IEC, NEMA, British standards, GB standards. So when they tell you to watch out for the invisible oven or to tighten up your support spans, you know it's backed by serious, rigorously tested engineering. So, the crucial point we keep coming back to is summed up perfectly in this quote directly from their 2026 guidelines. Ventilation, segregation, and support span are engineering decisions, not installation defaults. Just let that sink in for a second. You can't just unbox a cable tray, hastily bolt it up using the factory default width, and assume everything's going to work out perfectly. A data center is a living, breathing, physical ecosystem. Choosing an open window over a tight lid to let the heat out, setting up your 3-lane highway to stop signal interference, and tightening up that heavy clothesline for structural integrity, these all require active, smart choices by the people actually doing the work. Which brings us to our final thought today. Now that we've exposed the reality of that invisible oven above your hot aisles, the absolute necessity of letting the system breathe, and the massive structural payoff of just a half-meter adjustment, you really have to ask yourself, are your data center layouts built on smart engineering choices, or are you just relying on risky defaults? Next time you walk into a server room, take a moment to just look up. The answers are quite literally right above your head. Thanks for joining me for this explainer. I really hope exploring these practical analogies helps you build cooler, stronger, and much smarter infrastructure.